Welcome to this video on the binomial distribution part 1. After watching this video, you should be able to define the term binomial distribution, state the 4 requirements of a binomial distribution, and explain what x, n, p, and q represent in a binomial distribution. What is a binomial distribution? The binomial distribution is a specific type of discrete probability distribution that meets 4 main criteria. The first of these criteria is that there are 2 possible outcomes for every trial, which we call success and failure. Number 2, the probability of success is constant among all trials. Number 3, each trial is independent from the others. And 4, there is a fixed number of trials. All 4 of these criteria must be met in order for a distribution to be considered binomial. If even one of the 4 conditions is not met, then the distribution is not a binomial distribution. Quick note about success and failure. In everyday language, the word success has a positive connotation and the word failure has a negative connotation. However, in the world of statistics, this is not the case. For example, success might be defined as a person having a disease or testing positive for a disease, while failure could be defined as the person not having the disease or perhaps testing negative for the disease. Determining whether a probability distribution is binomial. Flipping a coin. Consider the example and determine whether each case is an example of a binomial distribution. A person flips the coin 5 times and records the outcome. Are there 2 possible outcomes? Yes, we can define success as getting heads and failure as getting tails. Or, of course, we could do it the other way around. It doesn't matter. The important thing is that there are only 2 possible outcomes. Is the probability of success constant? Yes, the probability of getting heads is 1/2. The probability of getting tails is 1/2. It's not important right now that we know what the probability is, only that we know that it doesn't change from trial to trial. We know that each coin flip is independent from the others, so therefore we can be confident in saying that the probability of success is constant. Are there a fixed number of trials? Yes, we are told that the person is flipping the coin 5 times, so there are 5 trials. Are the trials independent? Yes. Each coin flip is independent of the others. So therefore, since all 4 requirements have been met, we can say that this is an example of the binomial distribution. Let's do another example. Rolling a die. Consider the example and determine whether each case is an example of a binomial distribution. A person rolls a die 10 times and records the number that was rolled. So it could be a 1, a 2, a 3, a 4, a 5, or a 6. Are there 2 possible outcomes? In this case, there are not. There are 6 possible outcomes, so therefore we know already this is not a binomial. Anytime you're going through the requirements, as soon as you get to a requirement that isn't met, you can stop. However, for instructional purposes, I'm going to go through the other 3 requirements just so that you can learn and understand how to identify those as well. What do you think? Is the probability of success constant? Well, we're in a bit of a pickle here because since there are 6 possible outcomes, we can't really define one as success and the other as failure. So since we don't have an event that we're calling success, we really can't say that the probability of success is or isn't constant. There are a fixed number of trials, however, and the trials are independent. So even though these 2 requirements are met, since all of them are not met, we say that this is not an example of a binomial distribution. Let's do another example. Again, we want to roll a die. And this time, we say that a person rolls a die 10 times and records whether or not a 6 was rolled. So this time, are there 2 possible outcomes? So even though it's the exact same die, and the die still has 6 possible outcomes, 1, 2, 3, 4, 5, or 6, all of a sudden, we have grouped those 6 outcomes into 2 bins, if you will. We're going to define success as rolling a 6 and all the other numbers, the other 5 outcomes, as failure. So depending on how you word your problem is going to determine whether or not you have a binomial distribution. Let's keep going. Is the probability of success constant? So we know that if you have a fair die, the probability of getting any of those numbers is 1/6. So we can be confident that every time you roll the die, the probability of rolling a 6 is 1/6. Are there a fixed number of trials? Well, the problem tells us that this die is going to be rolled 10 times. So yes, there are 10 trials. Are the trials independent? Again, yes, we know that every time you roll a die, whatever happens is independent from what came before it. So each die roll is independent, so the trials are independent. So is this an example of a binomial distribution? And the answer is yes, because all 4 conditions were met. Okay, let's do another example about pacemakers. A person is tasked with determining whether each of 3,000 heart pacemakers is acceptable or defective. First of all, are there 2 possible outcomes? And the answer is yes, acceptable or defective. And you could define success as the pacemakers working and failure as them not working, or vice versa. Is the probability of success constant? Now, in this problem, we don't know what the probability is that each pacemaker is acceptable or defective, but we can say with confidence that the probability is constant because it's not going to change as you go through and test each pacemaker. Are there a fixed number of trials? Yes, there are 3,000 pacemakers, so you have 3,000 devices that have to be tested. Are the trials independent? Again, yes, because if you test one pacemaker and it doesn't work, that outcome is not going to affect the testing of subsequent pacemakers. So is this an example of a binomial distribution? And the answer is yes, because it meets all 4 criteria. Candy. You pick candy out of a bag and eat it, recording as you go whether each candy was your favorite color, which is blue, or not. Are there 2 possible outcomes? So yes, because you are dividing all the different colors, we're assuming there's probably more than 2 colors of candy in the bag, into 2 groups, which are blue, your favorite color, and some other color, not blue. So we'll call blue success and failure as any other color. Is the probability of success constant? Think about this really carefully. Pause the video and write down your answer and then unpause it to see if you are correct. So the problem here is that we're sampling without replacement. Let's say that there's 20 pieces of candy in this bag. Once you pick out a piece of candy and eat it, there's only 19 pieces of candy left. So you change the probability every single time you pick out a piece of candy and eat it. Now, as I said before, we don't have to keep going. As soon as we get a no, we can automatically say that this is not a binomial. But again, just for the purposes of instruction and teaching this concept, I'm going to go through the other 2 criteria. So are there a fixed number of trials? Yes. We know that there's probably a finite number of pieces of candy in the bag, however many that is. So the number of trials would be the number of pieces of candy that are in the bag of candy. And are the trials independent? No, right? They're not, because if you pick out a blue candy, you've changed the probability of getting another blue candy. And if you get a not blue candy, again, you still change the probability because there's a different number of pieces of candy in the bag than when you started. So is this an example of a binomial? Again, we already know the answer is no, because we did not meet all 4 conditions. Rolling a die, 3. You roll a die until you roll a 1. Are there 2 possible outcomes? Yes. So we're going to call getting a 1 success and any other number as a failure. Is the probability of success constant? Yes. The probability of rolling a 1 is 1 out of 6. Are there a fixed number of trials? What do you think? Well, not really. One person could roll a 1 on the very first roll. Another person could roll the die many times and still not get a 1. So at this point, we could just stop and say that this is not a binomial distribution. But again, for instructional purposes, we'll finish and do the last the last thing that we need to do. Are the trials independent? Yes, each die roll is independent. So even though we're meeting 3 out of the 4 requirements, because we failed one requirement, this is not an example of a binomial distribution. Roulette wheel. You spin a roulette wheel 8 times and make a note of whether it lands on an odd number. Are there 2 possible outcomes? Yes. We have odd or not odd. And you would normally think that I would say odd or even. However, there is one number that we have that's neither odd nor even, and that is 0. And depending on the sort of roulette wheel you are spinning, you might have 1, 2, or 3 zeros on the wheel. So the most precise way to express the outcomes is odd, or just to say odd and not odd. Is the probability of success constant? Yes, we're assuming that you are spinning the same roulette wheel each time and that the numbers on the wheel are not changing. So the number of odd numbers is staying constant. Are there a fixed number of trials? Yes, we're told that we're spinning it 8 times, so that's the number of trials. And are they independent? Yes. Every time you spin the roulette wheel is independent from the other times you're spinning it. So, is this an example of a binomial distribution? And the answer is yes, because we met all 4 conditions. Defining variables of the binomial distribution. We use a capital letter X to represent the binomial random variable. The binomial random variable X represents the number of successes in n trials and can assume many different values. The specific values X can assume are represented with a lowercase letter x. The letter N is used to represent the total number of trials, and the letter P represents the probability of success. Lastly, you might see the letter Q in some equations, and that represents the probability of failure. The probability of failure is equal to 1 minus P. Equation for the probability of an event in a binomial distribution. The probability of an event in a binomial distribution may be calculated using the equation below. Sullivan's textbook expresses this equation slightly differently. The notation, which is read n choose x, is shorthand for this mathematical expression right here. Also, the symbol q, as I stated on the previous slide, is the probability of failure, which is the same as 1 minus p. Therefore, although these 2 equations may look very different, they're actually mathematically equivalent. Let's explore this equation more thoroughly. You may or may not be familiar with seeing an exclamation mark in a math equation. In mathematics, we don't call it an exclamation mark, we call it a factorial. So the way we do this is 1 factorial is equal to 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so on. We also define 0 factorial as 1, which is important in some of these calculations that you will do. How to calculate binomial probabilities? While it is possible to use the above equation to calculate probabilities, it is, as you can imagine, time-consuming and cumbersome. Using this formula and performing manual calculations becomes even more cumbersome for inequalities, such as, for example, x is less than or equal to 4, where that expression would require you to calculate the formula 5 different times, once for each of the values x equals 0, x equals 1, x equals 2, x equals 3, and x equals 4. So you will be very relieved to know that in this course, you will be encouraged to use the binomial calculator in StatCrunch rather than evaluating this equation on paper in order to find the probabilities of a binomial distribution. Having watched this video, you should now be able to define binomial distribution, state the 4 requirements of a binomial distribution, and explain what x, n, p, and q represent in a binomial distribution.